So first important to mention is that we have as BASF a very important thing ahead of us, and this is decarbonization. We aim to completely decarbonize and aim net zero emissions by 2050. This is especially now tough now where we have very high energy prices, but we are fully committed to that. And actually, this is also very important to the battery material business because, as you know, battery contributes significantly to the CO2 footprint, and cathode active material is also a big part of that. Now talking about batteries, so also very important for, I think many, it's maybe not known for everybody, but we produce a lot of different components for EV packs already now. And this is very wide product range. So we produce in a lot of inactive components and like plastics and housings, but also we are producing components for cooling systems, and for sure the most important part is cathode active material. Let me just take a pointer. So talking about cathode active material, you know, this is still the component which defines the energy density of the battery and its costs and its safety. Now we have different requirements always for different applications, but essentially we can tailor our materials towards these applications, and our portfolio is containing materials which are NC, NCM, LMO, LCO, and manganese rich based. I will speak about that later on. We also are we are expanding continuously our production capacities, and meanwhile we are present in all major regions where we have our R&D centers to understand the customer needs and to serve the customers, because these needs are very different depending on the region. But the most important thing is that we have our production capacities everywhere, all over the world. And this is also very important because there are a lot of regulations which, let's say, set up the frame where you should produce, where you should source your cathode active material. And with this setup we have, we are quite good equipped for the future. If we look at the value chain, you know, there is the mining, raw materials, refinery, then we have cathode materials, and then we have cell batteries and OEMs. We are here in the middle of this value chain. What we do, we start with the precipitation, and we are making precursors. These are essentially hydroxides or oxyhydroxides, and then we calcine them, post-treat them, and we are getting our cathode active materials. And these materials then are used by cell manufacturers to build cells. But also very importantly is that we have now a pilot facility to recycle the battery packs. And this is operating in Schwarzheide, so that we can recover the metals out of the battery pack. Because first you get your metals for a reasonable price, which is not fluctuating. And second, your CO2 footprint is significantly better. Yeah, this is really a huge difference. And that's why we have now this pilot capacity, and we plan to build a recycling plant later. Now, if we look at the applications which we have now, typically we have EV applications. They drive the development of the batteries now, because just these are the volumes which we need there. And we have essentially entry segment, volume segment, and performance segments. And these, let's say, application have different requirements to cost to performance ratio. And for these applications, for all of them, essentially, we have our portfolio, which ranges from lithium manganese rich compounds They are cobalt free. 2 high nickel cathode active materials is more than 85% nickel. Here we have also different cell designs from cylindrical to prismatic cells. And it's also important to consider that not all these cell designs are compatible 100% with all these cell chemistries I'm mentioning here. But we are able to tailor that in the sense that it works well also in the pack level. And now the situation is even more complicated if we think about the arising technologies, which are novel cathode materials or new battery systems like solid-state batteries, sodium-ion batteries, and so on and so forth. And for this, we actively collaborating with different universities, and one very important collaboration is BELLA, which is Battery and Electrochemistry Lab located at the KIT. And here we explore actually all these topics here, but today I will talk about single crystal cathode material synthesis and solid-state batteries. First, I will start with the presentation of the topics which we have at BELLA. So what we do, we are synthesizing high nickel and novel cathode active materials with different stoichiometries and different morphologies. Like, for example, we make single crystal cathode materials, but also we are developing coatings for different applications. And here again, solid state batteries are very important because there you really need advanced coatings to make the material work. But also for sure the morphology is very important. I will also show some examples of how morphology affects the solid state battery performance. We are also look at the system level, the cell level, how the solid state battery are working, investigating the fundamental properties of solid electrolytes and cathode materials. And we are traditionally very well equipped with analytics. We have some methods which we have developed on our own, like for example, differential electrochemical mass spectrometry or gas flow reactor for in-situ diffraction, and we are actively using them. But also operant acoustic emission actually started being developed by Simon. So method which we're really actively using now. This is the overview of the research, and now talking about specifically solid-state batteries. You know, just briefly, the advantage, I think the unique thing about solid-state batteries is that potentially you can have very high performance, high energy density, and also you can potentially be quite safe in terms of thermal propagation and risk of fire. Yeah, just because you're using non-flammable electrolytes. And this is for sure really unique. So safety, high safety and high performance, this is what would be a dream to have. And actually the costs are also quite attractive because you have high energy density. So in terms of dollar per kilowatt hour, you are quite good because your kilowatt hour number is just huge here. But for sure, there are a lot of challenges for this technology. And first, the challenge is mechanics of the solid state batteries. Here, what is typically happening, you have contact losses between cathode active material and your electrolyte. It happens because of volume changes of the material and also because of cracking. And another thing is that most of the high conductive solid electrolytes, they are actually not stable in the potential range you are operating typically. And you have actually more interfacial reactions than in conventional lithium-ion batteries. And finally, you always have more issues related to the ion transport in solid-state battery systems because you have a tortuosity problem in the high loaded electrolytes. And this problem is strongly dependent on the cathode active material particle size, which is not the case for conventional lithium-ion batteries. So here you also have to consider the particle size of the secondary particle. So a lot of things to consider, a lot of challenges, but let us go start with the mechanics. So, you know, there are very nice publications showing the phenomena which are happening in solid state battery during cycling, during lithiation and delithiation. What you can typically observe is, like shown here, detachment of the secondary particle from the solid electrolyte. You can observe intergranule cracking if you make a cross section of your cathode active material, but also you see sometimes intragranule cracking, so that you see that your crystallites really break. And you even observe sometimes infiltration of solid electrolyte into these cracks, which is actually very interesting. Now, why it happens? Well, you know that the high nickel material, but actually also NCM material and LCO, they all experience certain volume changes during the charge and discharge. And these volume changes, they are of anisotropic nature. During the charge, you have two crystallographic axes, A and C, and A is contracting, C is expanding, then C is contracting again. So you have a lot of different changes, and in this polycrystalline particle, like shown here, for sure, you have a lot of strain, which leads to the to this cracking between the particles. And because of this strain, probably you also have intragranule cracking, so that even single crystallites can break. Now, how to deal with that? Now the second slide would be about the interfacial problems. Here's an example of lithium nickel oxide. And here you see the measurement which is conducted using lithium nickel oxide in conventional battery, shown in yellow, and you see a measurement conducted with the lithium nickel oxide in a solid state battery. Both of these materials are uncoated, and you see that for the conventional lithium-ion battery, you achieve around 93.8% of coulombic efficiency in the first cycle, meaning that essentially most of the lithium you are getting out of the cathode active material you can really put back in. Now, if you compare this yellow profile to this green voltage profile, you see that first of all, the coulombic efficiency is much lower. It is just 72.2% in the first cycle, meaning that there's a lot of losses of somehow lithium, active lithium, which you reintercalate, but also the charge capacity is quite low. Yes, and for sure the discharge capacity is very low. It's 150 milliamperes per gram. Interestingly, if you make DEMS measurements, so the analysis of the gases which are evolving from these two type of cells, you will observe that actually the gases which are coming out of the lithium nickel oxide in solid state battery, they are really negligible. So if you compare these solid state battery and the gases coming out, they are actually much less than what you would observe in conventional lithium-ion battery. And this is actually already very interesting. So the question is, what is happening? And here XPS is surprisingly kind of helpful. So what you see essentially is that you see arrival of very many additional peaks in the solid electrolyte, or at the interface of solid electrolyte to CAM. They are marked here by red and orange and green. And you observe two types of species here. These are polysulfides and thiophosphates, but also you observe oxygenated species like SOX, SO3, SO4 anions, and POX species. And now if you think about where the oxygen is coming from, for sure this is only possible if you get it from the cathode active material, from LNO in this case. And this means that you form really, you're taking oxygen out of LNO, or all the LNO is releasing the oxygen, and it's not forming gas as in conventional cell, but it is reacting with your solid electrolyte. It forms sulfates and phosphites, which are even kind of conductive. But the problem is that your lithium nickel oxide is really evolving towards nickel oxide at the surface, and this is not conductive layer, which is resulting in such poor performance even the first cycle. So you see this interfacial phenomena which are destroying your cathode active material already in the first cycle. Now, if you think about what kind of effect you would have if you take different cathode active materials of different size, here's a very nice study conducted by Florian Strauss, where he used different polycrystalline NCM622 materials with a size ranging from 4 microns to around 16 microns. And he built solid state batteries and conducted just first initial charge-discharge measurements and observed huge differences. And what you essentially see here is that you cannot achieve proper capacity if you take large particles around 60 microns. The charge capacity is below 100 milliamp per gram. The discharge capacity is below 50. It's very low. Then you move towards smaller particles, and at some point, the capacity is getting better. And why is that? This is actually very interesting. If you conduct the measurements of ionic and electronic conductivities of all these three tapes, then you see that first of all, your ionic conductivity is actually not very different here, probably because you use the same solid electrolyte, right? But your electronic conductivity is very different and is kind of very low if you use such large particles. So here the percolation is really very important. Now, how can we deal with this first phenomenon which I mentioned, which was surface phenomena or interfacial reaction? What we can do, we can use surface coatings and apply them onto our uncoated cathode active materials, for example, using ALD. Then you can form a thin zirconium oxide layer around 4 nanometers, and then you immediately see an improvement in the cycling in the solid state battery. You have better capacity retention, and you have actually also better charge and discharge values already in the very first cycles. There are other techniques, like you can also use nanoparticles. This is a very nice method developed by Yuan Ma here at BELLA, and he has prepared zirconium oxide nanoparticles, suspension, and immersed the cathode material into it. And then you can see in TEM very nice layer formed out of these small nanoparticles. And this layer seems to be quite homogeneous, as shown here in ADX mapping. And you see immediately improvements in the cycling behavior. Actually, very similar effect as we just saw for the ALD coating. Now, if you switch a little bit to the mechanics of the cathode active materials in solid state batteries, there are different volume changes which cathode active material experience, and they are plotted here depending on cobalt to nickel to cobalt ratio. You see here different NCM materials and also LCO, and there's a line which is quite straight, and you have, let's say, positive volume change for LCO, and you have a negative volume change of NCM 811, which is nickel rich material. So this is during the charge, during the dilithiation. And now in this line, you can spot a point where you essentially have zero volume change. And this is a nice work done by Florian Strauss. And I think this idea was from Pascal Hartmann, essentially, where you are making such a material, which was really synthesized, to achieve zero volume changes in the solid state battery. And how do we do that? Well, you know that these materials, they have two crystallographic axes, and one axis shrinks during the charge and another expands, and you can tune them in the way that they are just compensating each other. And if you then build a solid state battery and measure the pressure during the cycling, then you see that for both these materials, so these are NCM271 and NCM361, you actually do not measure significant volume changes during the charge and discharge, which is very nice. Another thing, if you think about the mechanics, you can use polycrystalline or single crystalline materials. And if you just compare, here is a study where you compare similar chemistries of 83% nickel and 85% nickel, and you compare the behavior of these materials, which are both uncoated in a typical solid state batteries, then you see very interesting things. First, the single crystal material delivers much higher capacity than the polycrystalline material, which is actually untypical in lithium-ion battery. The liquid electrolyte, this is other way around. And you're also getting better capacity retention. And now if you monitor again the pressure of your solid-state battery, surprisingly, we see that the cell with a single crystal material in the blue line here, it has less volume changes, or sorry, less pressure changes during the charge and discharge, although you have actually higher capacities. And also the profile looks kind of more symmetric. And finally, if you open these cycled cells and look into the morphology, then you see that the polycrystalline materials really cracks a lot after the cycling, and the single crystal materials remains much more intact. Now, I would like to switch a little bit to the gears and speak about single crystal materials in general, and why they are interesting, and we think that they are really promising, and why it is important to develop them and also to make research on them. So first of all, these materials have actually the crystallographic density, which is very high. It's 4.0 gram per cubic centimeter, which is much more than the typical density of polycrystalline samples, which is just 3.5. The cell manufacturers, they require at least 3.5 gram per cubic centimeter electrode density, and I have to say you that it is actually impossible to achieve it with the only polycrystalline samples. Even if you tune the particle size distribution, use bimodal systems and everything. So you need at least a component, which is single crystalline, to fill the gaps of your polycrystalline electrodes to increase the density. Otherwise, it's just not possible. And this is actually also interesting that in the polycrystalline electrode, you have just closed sphere packing, right? And there you have gaps up to 30% of your volume. And these gaps are actually either tetrahedral or octahedral. So if you tune your single crystal in terms of shape and size properly, then you can actually fill the octahedral gaps of polycrystalline electrodes using your single crystal. And this cartoon here, it's for sure it's just cartoon, but actually it's a quite real shape of the materials which you can make if you use proper synthesis. So in terms of density, this is really amazing what you can achieve with the single crystals. And another thing is for sure is stability. You have no grains inside ideally, and you have no intergranular strain. It means that you do not have cracking during the cycling, which I just described before. Now, for sure, there are challenges associated with the synthesis of these materials. First of all, you are in the size of 3 to 5 microns typically, and this is for sure it's huge compared to what lithium has to diffuse if you look at the conventional materials. In the polycrystalline materials, you have a crystallite size around 200 nanometers, and here you're like around 5 microns. So it's order of magnitude more. Lithium has to go through this bulk, and for sure you have limitations in terms of lithium diffusion. Then another thing, if you have additionally the nickel and lithium sides just within the lattice, then you have even more problems kinetically. Another aspect of these materials or challenge is that you typically use high temperature sintering, And if you do that, then it is not always easy to size tune these materials because you have temperature variations and the size is very sensitive to the temperature at the end, especially in the large scale. And for sure, if you go to high temperatures, you're more expensive. So single crystal materials are typically more expensive than the polycrystalline ones. And now, if you put all these problems together, especially like kinetics, lithium-nickel exchange, and high temperature, you can imagine that actually going to high temperatures, you're inducing lithium and nickel sites and a lot of defects. So you have to go for that, for sintering, but as a side effect, you're really getting problems with kinetics. Yeah. And this is what we're trying to optimize, let's say. So the idea of a study conducted here at BELLA was to make a perfect or as perfect as possible lithium nickel oxide, which is single crystal and which has lowest lithium nickel exchange possible. And this is very tough because especially for lithium nickel oxide, you have always the problem that nickel is going into lithium sites during the synthesis, just because they have similar ionic radius. So, and there, the idea was to start with something where you do not have such a problem. And this is idea of Leonard Kager and Daniel Weber. And here the idea was that we start from sodium nickel oxide, where you have very large sodium, iron, and just your nickel, right? And they just do not intermix. And this is what we did. So we have synthesized sodium nickel oxide first at different temperatures. And you see here the micrographs from 400 to 750 degrees. You can make single crystal sodium nickel oxide. And you can actually already here perfectly size tune this material. So you see that the size at 400 degrees is around 1 micron, and if you go to for 750 degrees, then your size is around 4 to 5 microns. And this is really very nice. And then, well, the question is how to make LNO out of that. So what was done here was ion exchange using lithium nitrate melt, and this is also very nice setup, which is gas flow reaction for in situ diffraction setup developed also by Daniel Weber and Matteo Bianchini, which essentially allows you to monitor your diffraction patterns during the synthesis. So you have your capillary, and this capillary is in the XRD beam, and you are recording your diffraction patterns during the synthesis. In such a case, you start with sodium nickel oxide. These are these intense reflections here. And you have your lithium source, your lithium nitrate salt. And then you go, you're just heating up your capillary. And this is actually very interesting. If you look what is happening here, if you look at these first reflections, which were assigned to our starting material, which is sodium nickel oxide, you see that there's a new reflection, which is forming already at quite low temperature. I think this is something around already 120 degrees. And this is actually a kind of dissociated sodium nickel oxide, which forms at low temperature where nothing melts. Yeah. And here you also see that lithium nitrate reflex is losing its intensity, and there is a new reflex, which is sodium nitrate. So it taken together, it means that there is a sodium which is coming out of NaNO, so out of sodium nickel oxide, and there's lithium which is going in. So the ion exchange starts already at very low temperature, where everything is still kind of crystalline. And for sure, then at some point, this is around, I think, somewhere below 200, I think 180, everything melts, not everything, but your salts, lithium nitrate melt. And you see that the sodium nickel oxide phase is disappearing, and then we see formation of our lithium nickel oxide, which is then kind of finished at around 260 degrees. If you then take out the sample and wash it, you will see your single crystals, which are now lithium nickel oxide crystals, which have the same size and essentially the same shape as you had it before for sodium nickel oxide. Surprisingly, the surface looks quite clean. Although we have to wash the material, we have layered structure at our LNO surface. And now if you characterize this material, first, what is interesting to see for sure, we are talking about lithium nickel exchange, and it is very interesting to make NMR, which was done here by a group of Silvio Indris, where you essentially compare your ion exchanged LNO sample with the conventional LNO samples made by solid state synthesis, where you go to really high temperatures. And these samples, they are here in red. They have different lithium to nickel exchange from 2.9% to 5.6%. And if you look at the NMR signal at around 700 ppm here, then you see that this peak is increasing with the decreasing nickel and lithium sites. And the signal is the highest for our ion exchange sample, which is already indicative that we are very low in the nickel and lithium exchange here. Also, XRD confirms that we have no nickel and lithium sites. And interesting feature here is this shoulder around, I think this is around 480 ppm, which is indicative for nickel 2+ around lithium, and basically you do not see this signal for our ion exchange sample at all. And this is a good news. We have really managed to make ion exchange lithium nickel oxide, which has no nickel on lithium sides. Yeah, and this is, I think, for the first time. I have not seen such a material before in the literature, which is very good. Now, rather bad news for, let's say, product development is that this material, although it has no nickel lithium exchange, it performs very badly in the cell. So if you compare it to the conventional LNO material, our ion exchange sample has low charge capacity, and it delivers only around 175 milliamperes per gram of the discharge capacity. So why is that? Well, the answer is actually here. So if you look at the cross-sectional TM, then it's a certain orientation, which is here essentially chosen in the way that you see the lithium diffusion planes. You see everywhere a lot of cracks, meaning that if lithium is, let's say, trying to diffuse in or out, it stops at some point because there will be a crack on the way. And this severely limits the diffusion. And why is that? Well, I have to say that these cracks are not visible in the sodium nickel oxide, which we used as a precursor. So they really appear after ion exchange. And if you then remember that sodium nickel oxide has other space group, it's monoclinic, and our LNO is rhombohedral, then, well, there is a change in the lattice, and this change or strain vector is actually oriented in this direction, and in this direction we are experiencing the cracking. So the ion exchange leads unfortunately to such a strain, and then we have a lot of cracking in our material, which limits our electrochemical performance. Now I'm already at the end of my presentation, so just to sum up. So first of all, as I mentioned, cathode active material chemistry and battery design, they are really a key now for the battery energy density, which affect weight, range, and safety. We as BASF offer tailored cathode material solutions to meet the performance target, cost targets, and so on. And we are very active in also developing next generation cathode active material and do a lot of research here. And Battery and Electrochemistry Lab BELLA is a fundamental collaboration here. And I just have shown you some of the BELLA studies, which show what is the potential of solid-state batteries with high nickel cathode materials, and also have shown you some of the results on single crystal materials, which I think kind of new and interesting. And finally, I would like to thank all the BELLA members and all the collaborators. So thank you very much.